What is the shortest path between 2 points? If you ask anyone on the street, they'll tell you the same thing. A straight line. It's an idea so deeply wired into our brains that we treat it as an absolute truth of the universe. In physics, it's how light travels through a vacuum. In architecture, it's how we measure boundaries. But in mathematics, this straight line distance isn't a fundamental law. It's just one choice out of infinitely many. Before we write down any equations, what exactly is a metric? In mathematics, a metric is just a fancy word for a distance function. It's a rule that takes 2 points in a space and hands you back a single number representing how far apart they are. But for a rule to define a valid metric, it must satisfy 4 strict logical laws. The first law states that the distance between 2 points A and B can never be negative. When we measure the length of an object with a ruler or scale, the number we obtain is always non-negative. The second law states that the distance from a point to itself is 0. This law is self-evident. The third law states that the distance from A to B equals the distance from B to A. In other words, the measured distance is invariant under exchange of the endpoints. It does not depend on direction. The last law is the triangle inequality. It says that going directly from A to B is always shorter than or equal to taking a detour through a third point C. If your distance rule satisfies these laws, congratulations, you have a metric space. The metric we use every single day, the one that gives us our physical intuition of space, comes from ancient Greece, credited to the father of geometry, Euclid, and it is called Euclidean Metric, and its mathematical engine is a theorem you probably learned in middle school, the Pythagorean Theorem. Let's formalize this. Suppose we have 2 points, A and B, in an n-dimensional real space, Rn. Each point is defined by its coordinates. The Euclidean metric in an n-dimensional space, that is, the measure of the distance between the points A and B, is given by the square root of the sum of the squared terms. This implies that even if we don't know how to represent the object in n space, we can find the distance between 2 arbitrary points in that space. We can perceive only 0 to 3 dimensions. Points, lines, planes, and 3-dimensional objects. In 1 dimension, just a simple number line, the Euclidean distance is just the absolute value of their difference. As we can see, it doesn't matter if we from A to B or from B to A, the results are the same. In 2 dimensions, on a flat plane, we construct a right triangle between the points. The horizontal distance is x2 minus x1, and the vertical distance is y2 minus y1. Squaring them, adding them together, and taking the square root gives us the familiar hypotenuse, and it is clearly linked to the Pythagorean theorem. Now, if you look deeper into linear algebra, you'll find that the Euclidean metric doesn't just sit there on its own. It is actually induced by 2 deeper algebraic structures, the norm and the inner product. From linear algebra, we know that a vector space can have a basis made of independent vectors, such as I and j. These vectors are independent because neither one can be written as a combination of the other vectors in the basis. Also, they have magnitude equal to 1, which is why they are called unit vectors. Using these 2 important properties, we can represent any vector as a combination of these basis vectors multiplied by scalars, or real numbers. For example, the vector w can be written as the sum of 3i and 2j. This means that the vector w has a displacement of 3 units in the positive x direction and 2 units in the positive y direction. In this way, any vector in a plane can be represented using the basis vectors I and j. Look at the geometry. The tail of the vector is located at the origin, where the coordinates are x equals 0 and y equals 0. The head of the vector reaches the point at x equals 3 and y equals 2. Here we can see an important connection between vectors, the Euclidean metric and the norm. The distance from the origin O to the point A is exactly the length of the vector W. This length is called the norm of the vector. The norm gives us the magnitude of a vector, and like a distance, it is always non-negative. Another important mathematical tool related to the idea of Euclidean metric is the dot product, also called the scalar product. The dot product is an operation that takes two vectors and produces a single number. Geometrically, it tells us how much two vectors point in the same direction. For two vectors u and v, the dot product depends on the angle between them. If they point in similar directions, the dot product is positive. If they are perpendicular, the dot product is 0. If they point in opposite directions, the dot product is negative. Now, something interesting happens when we calculate the dot product of a vector with itself. The result is the square of the vector's magnitude. Taking the square root, we find it. Therefore, we discover a beautiful connection between three mathematical ideas. The Euclidean distance, the norm of a vector, and the dot product are all connected through the same expression. This relationship shows how geometry and linear algebra describe the same underlying structure from different perspectives. A clear application of the Euclidean metric is found when we build the equation of a circle. If we are working in 2 dimensions and considering 2 points, C and P, on the plane, we can derive the equation of a circle. If you remember, a circle is a mathematical object defined as the set of all points at a constant distance r from a fixed point C, called the center. By applying the Euclidean metric, we obtain the equation of a circle whose center is not necessarily at the origin. When the center is at the origin, the coordinates C1 and C2 are equal to 0. Throughout this video, we have explored one of the most fundamental ideas in geometry, the Euclidean metric. From it, many important geometric objects can be constructed. Lines, spheres, angles, and many other concepts of classical geometry are deeply connected to this notion of distance. But the importance of this metric goes beyond geometry. It provides the foundation for much of mathematics, physics, engineering, and our understanding of the physical world. Whenever we measure length, calculate trajectories, design structures, or describe the motion of objects, we are using ideas that come from this metric. The Euclidean metric is more than a formula. It is a way of understanding space itself, a bridge between abstract mathematics and the reality we experience. And this is the beauty of mathematics. From a simple definition, such as measuring the distance between 2 points, an entire universe of ideas can be built. Thank you for watching. Hit the like button and subscribe for more. God bless you.